Welcome back. Today we're going to discuss the difference between temperature and heat. Now, in the summertime, the outside temperature might be very warm, and there is obviously a lot of heat that makes that, but they're not the same thing. We want to discuss how are temperature and heat different, and so by the end of this discussion, hopefully that'll be more clear to you. So we measure temperature using an instrument called a thermometer. Well, how do we measure heat then? And I know some of you are saying, well, you also use a thermometer. Well, in fact you don't. Instead you would use an instrument called a calorimeter. And we'll discuss again what is the difference between temperature and heat. Okay? So let's start with let's compare and contrast, or at least compare Celsius and Kelvin temperature scales. Most of us are familiar with the Celsius or centigrade scale. Water will freeze at 0 degrees Celsius and it will boil at 100 degrees Celsius, and there's 100 degree units between those two. And that's a pretty easy, convenient scale for us to use. If you were to drop the temperature down to the coldest possible temperature, it's called absolute zero. Now, that corresponds to about negative 273 degrees Celsius, or about negative 470 degrees Fahrenheit. So why do we call that temperature absolute zero? Well, the Celsius is a convenience scale based upon the Kelvin scale. The Kelvin scale, water boils at 373 Kelvin. Water freezes at 273 Kelvin, and the coldest possible temperature is 0 Kelvin, or absolute zero. I'll point out a couple things here. There is no degree sign on the Kelvin scale. It's an absolute scale. If you add degree Kelvin, I probably won't mark it wrong, but please know there is no a degree mark for Kelvin. There is also no such thing as a negative Kelvin temperature. The coldest spot in, as far as we know in the universe, in outer space, is maybe 2 to 4 Kelvin. There is nothing where it is negative 8 Kelvin. It doesn't exist. Now, you could ask a physical chemist and they could probably give you a good explanation of why that is, but let's just assume that all motion stops at 0 Kelvin. So I'm going to define temperature as the average kinetic energy. Now, I do a lot of photography, and there's something called the shutter speed, and it's how quickly the shutter opens and closes. And if you take a very long shutter speed picture where you open it goes click, click, and it's open for a second or so, anything moving across the frame is going to be a big blur. So how does that relate to what I'm talking about with temperature? Well, look, this is not line segment KE. If we were in math class, maybe that's what it means. But here, the line above it means average kinetic energy is mathematically defined as 1/2 mv squared. M refers to the mass of the substance, v its velocity. Now, some of you are going to take physics and study about vectors. Vectors give direction and magnitude. Let's imagine this. I have a red dot here and a blue dot here, and I tell them both to run away at the same time. I say, ready, set, go. And I say, stop. The red one travels this distance, while the blue one only travels this much distance. Clearly, the red one is moving faster. What gave it the energy to move faster was the heat that it possessed. So if it is moving at a faster average temperature, or average speed, we say it is the hotter of the two molecules. So in this case, the faster you move, the hotter you are. That's how we're thinking about this. Now, imagine, I'll put my arm up here, this is thermometer, and you go to the carnival where they give you the hammer and you get to swing the hammer and hit. So let's try it this way instead maybe. So as you hit, as hard as you can, you cause the little bell to go up and go bing, and it rings because you hit it really hard. Now, maybe when your friend hit it, they're not as strong as you are, so when they hit it, it only goes up a little bit and it says wimp, and then it falls back down. Now, what this analogy represents is a thermometer. The air molecules in the room are moving very slow hitting it and very fast hitting it. And it's picking up the average speed of the molecules. The faster they're hitting the thermometer, the little bulb at the bottom, the farther up the liquid goes in the tube. So it truly is measuring a thermometer, the average kinetic energy in the room. Now, there could be very slow, cold molecules in the room, as well as very hot molecules in the room. I suppose if we want to try to explain spontaneous combustion, we could imagine a person sitting there and a bunch of the hot molecules, fast molecules, land on them and poof, they burst into flames. Now, if that were true, it would be just as plausible that a bunch of the cold molecules would simultaneously land on the person and they would be frozen solid in a catatonic frozen position. Neither of those things happen. It's an average. The probability of that happening where all the hots or all the colds were to land on you at one point are infinitesimally small, right? In other words, it's not going to happen. Now, we have some idea what temperature is. I'll try to explain it in a few other ways for you here. But let's just compare the different temperature scales. We've already looked at the Kelvin scale versus the Celsius scale. Here's the boiling point. Water boils at 100 degrees Celsius, 373 Kelvin. Water freezes at 0 degrees Celsius, 273 Kelvin. On the Fahrenheit scale, the one that most of you grew up with, water would boil at 212 degrees Fahrenheit. Now, I bet there were half of you did not know what temperature water boils at on the Fahrenheit scale. I'm pretty sure you all knew that water freezes at 32 because that's a number we see frequently, but you don't always see the boiling point at 212. Notice that a Fahrenheit degree is a smaller unit than a Celsius degree, and a Kelvin degree, there's 100 units between freezing and boiling for these two, but 180 between these two. So clearly there is a conversion we can go between Fahrenheit and Celsius and Kelvin. And we'll practice those conversions as well. Maybe you've heard of the Kelvin scale. If you do video and you make any video and you have to light it properly, you're worried about the color of your lights that you're using. And if you buy fluorescent bulbs can either be daylight fluorescent, where maybe you've gone by a neighbor's garage at night and their garage door's open, they have the light on, and it looks like nice, bright white light. They are probably using a 5250 sunlight blue colored bulb, or it might look a little bit more yellow or even green colored depending on the spectrum of the bulb that's being utilized. A regular incandescent light bulb is simply a glowing filament, and it tends to be sort of a orangish brown color. If you were to shoot a picture without a flash on film, that's what it actually sees. Your eyes tend to autocorrect that and make things look the proper color, but film doesn't have a brain to do that, so the color of light matters immensely when you're looking at that. And it's measured in a Kelvin scale, so that's another spot maybe you would have heard that. Now, this number does not correspond to a temperature. It does not mean that that bulb is 5,250 Kelvin degrees. Okay? It's just the color of the light. We've already hit this pretty well between Celsius and Kelvin. The only addition is we see here on the Fahrenheit scale where absolute zero or 0 Kelvin corresponds. Negative 273 Celsius, and again, about negative 460 degrees Fahrenheit. That is really cold. Now, I would give you a little warning when we do make those conversions later on. If you get a value of a Fahrenheit temperature below negative 460, like negative 512 Fahrenheit, that answer has no meaning. Your calculator will make a conversion for you, but you have to understand what the number means. Okay? All right. If you want to convert between Fahrenheit and Celsius, there's your formula. Take your degree Fahrenheit, subtract 32, and divide by 1.8, and you will get the corresponding Celsius temperature. I probably won't have you do that for me on a test, but it's a relatively easy conversion to do. If you want to convert from Celsius to Kelvin, that's a conversion I will want you to do. It's simply take the Celsius temperature and add 273 to get to Kelvin. Likewise, if I give you Kelvin and I want you to give me degrees Celsius, simply subtract 273, and you can go between the two. All right, just a few thoughts here. Temperature can be kind of subjective. I was at a cross-country meet yesterday, and a lot of the kids were sweating profusely and complaining how hot it was. Now, I wasn't running, so I thought it was relatively comfortable, a very nice day, because the humidity wasn't bothering me as I was just sitting there and watching. So temperature is subjective, and therefore we have to have a scale to measure how hot it is. So we know where the boiling point is, we know where the freezing point is, and originally on the original Celsius scale developed by Andreas Celsius, he was going to make the freezing 100 and the boiling 0. Now, upon his death, everybody thought that was stupid, and they changed it and made freezing 0 and boiling 100, which is the way it is today. You're familiar with a Fahrenheit scale, because that's the one we've grown up with. It oftentimes uses a chemical in there called mercury. It's a silver gray metal. It's somewhat toxic, and if your thermometer is maybe green colored liquid or red, that's an alcohol with a dye. Those tend to be a little bit safer. Or nowadays we're so familiar with the thermal one where they hit you in the forehead or they aim in your ear with it and then get your temperature that way as well. And mercury and alcohol thermometers rely on thermal expansion. When things heat up, they tend to expand. So perhaps you've seen a sidewalk when it gets really hot, or a road, if it's made of concrete, it will develop cracks in it. Now, the way they try to mitigate that is they put these expansion joints in there so that when the concrete expands, it can expand and it has space in between it. Or maybe you've seen a bridge where if you look down at the bridge, there are what are called finger joints. And they generally look like this. And then when it's hot, the two halves, the left and right hand of the bridge, move closer together. And when it's colder, they tend to contract and they go a little bit farther apart, but the bridge is held together. Even our own school, outside my room in the hallway, there's a giant expansion joint because Normal Community High School is a very long building and it needs to expand and contract without cracking. So large structures like bridges will have these thermal expansion joints put in them, and so that way you won't develop those cracks. Water is a bit of an exception to this. When water freezes, water expands. It's probably the only substance that expands when it freezes. There could be others, but I'm not aware of them. So as a general rule, when things heat up, they expand. When they cool, they contract. Water is our only exception. Now, if we were to look at and visualize what water looks like, it's in constant motion at the molecular level. So if we have hot water on one side and cold water on the other side of this box, and we have a divider, a thin metal wall, if I were to pull that divider out, what I would see is the water molecules on the hot side are moving faster. See, there's a longer vector, a longer tail, meaning they're moving faster than the cold water where the tails are a little bit shorter and they're not moving as fast. Now, I could certainly visualize this. This would be an experiment you could do at home. You could take a glass of hot water and a glass of ice cold water, and then simultaneously add a drop of food coloring to each, and then don't stir them. And I think what you'll observe is the hot cup of water, the food coloring will dissolve very readily and the entire cup will be uniform color pretty quickly. Where in the cold water, it'll take substantially longer for that food coloring to mix if you don't mechanically mix it or stir it. And again, what you're witnessing, what you're seeing is the molecules moving at the atomic level. Hot molecules move faster, cold molecules move slower. If we were to look at the same temperature water on both sides, the vectors would be the same. And if this was a perfectly insulated box, if I started with 90 degrees here and 10 degrees here, and no heat escaped from that system, over time I would expect that both sides would be 50 degrees Celsius if no heat left the system. Alright, so we keep dancing around that heat and temperature aren't the same. Let's see if we can explain it this way. We're looking at kinetic energy. That's energy of motion. Remember, when the molecules, if this was my thermometer, when the molecules strike the side, they cause the molecules to go up higher. The faster they hit, the higher up they go. That's the energy of motion I'm referring to. So what causes molecules to move? Energy. Energy in the form of heat. So if I look at, let's say I am boiling some water, a pan of water, I will get some of the water molecules to move very, very fast, the ones at the bottom of the pan next to the flame. And others near the top might not be moving as fast, and I get this rather bell-shaped looking curve. So I got fast-moving molecules out here, slow-moving molecules over here. And if I look at how many molecules were moving at each speed, I could count them up and make a point, and I've connected all those data points. I'm going to call this the average kinetic energy. I know I didn't do a very good job of that. The average probably would be closer to somewhere over here, but let's just call that the average kinetic energy. The average speed of the molecules is what we call temperature. Now, if I were to heat that water up a little bit more, it would change the look of the curve. Notice the curve now got not quite as high, and it got a little bit broader. That's a higher, hotter molecule. And the average is a little farther out. See, the higher temperature has a higher average kinetic energy. The lower temperature has a lower kinetic energy. Now, if I were to add up all the area under that curve, the total kinetic energy would be heat. In other words, it took a little energy to get these molecules to move, a little energy to get these molecules to move, and all of these molecules took energy to move. Let me explain it another way. Let's assume that you have a house and you have a couple choices in the summer. If you have an air conditioner, you can let it run all the time, or you can turn it off when you leave the house and turn it on when you come back. Now, it turns out that leaving it on all the time will probably save some energy. Now, you can turn it up a little bit so it's not quite as cold, but there is heat trapped in your floor. If you have carpeting, there's heat in the draperies, heat stored in the chair that you sit in. And so there's heat trapped everywhere. And when you turn your air conditioner on, it has to pull all of that heat, that stored energy, out of the room before it allows the room to cool off and feel a colder temperature. So another example might be your refrigerator. In the wintertime, maybe you have a cat. The cat would like to sit at the base of the refrigerator because a refrigerator is nothing more than a heat pump. It takes the heat that's inside the refrigerator and it removes it to go outside of the refrigerator, and it blows out the bottom and warm air comes out the bottom. Now, if you think you could cool your house by simply opening your refrigerator up and letting it run all day long, you're mistaken. What it will do is it will take the warm air in the room and it will cool it in the refrigerator and pump the warm air out back into the room. So all you're doing by leaving your refrigerator open in an attempt to cool your room is costing yourself lots of energy. and it will not cool the room at all. All right, let's see how else we can look at this. If we were to look at the speed or velocity of the molecules of the room, if I took a random sampling of the molecules in the room, I'm going to have some of these molecules that aren't moving at all, barely moving, or are moving pretty fast, like some of the red ones. And if I were to graph that speed or velocity, I find out I have some very slow ones, some relatively fast, and some super fast molecules. So if I sort them by speed, remember speed has to do with average speed is the temperature. So if I were to graph that, I would end up with our little curve that we saw earlier. And then if I call this the red line the average speed, then that would be the temperature. Average kinetic energy is temperature. This is referred to as the Maxwell speed distribution. You don't need to know that at all. And so we've got, again, slow moving and fast moving molecules. The average speed of the molecules is what we call temperature. So let's see if I can summarize this for you using our friend the double bubble mind map. Temperature versus heat. Well, they both have to do with kinetic energy. Total kinetic energy is what we call heat. All the energy of all the molecules in the room. That's the total amount of heat energy that it took. And temperature is the average kinetic energy of those molecules in the room. Look, you can take a heat gun that might be 800 degrees and you can accidentally touch it and only touch it for a second, or only leave that gun on for a minute. That heat gun, will not heat up an entire room because the room has too much thermal mass to heat up. You're only going to get the molecules right near the heat gun to heat up very fast and change their temperature. Both of these, heat and temperature, are a property of matter. Heat is measured with an instrument called a calorimeter. When we're done with this unit, we'll do a little mini unit on calorimetry. The unit for measuring heat is joules or calories in the English system. Temperature, on the other hand, is measured with a thermometer. Temperature, as we stated, is an average speed or average kinetic energy of the molecules in the room, and it's measured with a unit of degrees Celsius or Kelvin. Let me try to give you another comparison example. If you have an air conditioner in your house, it might work very well in your house. But let's assume that the high school's air conditioner went out, and we took your air conditioner from your home that's working perfectly fine, and we put it in normal community and made that the only means of cooling the school. You would determine and figure out pretty quickly that that school was going to get very, very hot because you cannot remove enough heat energy to cool the temperature of the school down. Likewise, if you have a furnace and you turn it on and you have a very big home, your home will be rather comfortable. If you leave that furnace burning the same amount and you put it in a very small house or small room, you'll think, wow, this room is way too hot because you've added too much heat energy into that small space. So I hope you start to understand the difference between temperature and heat. Thanks for joining me, and we'll continue our discussion of matter and energy in our next lesson. Bye-bye.